Okay, we are going to get the ball rolling. So without further ado, please welcome our moderator for today, Dr. Eric Rowe. Dr. Rowe is the Executive Director of Texas Engineering Executive Education, the Continuing and Professional Education Unit of the Cockrell School of Engineering at UT.
Thank you, Javier. As Javier mentioned, welcome to our webinar. This is the first in our series of Cockrell School of Engineering TexTalks, where we're hoping to bring to you some of the exciting research that's happening at the Cockrell School of Engineering, as well as some of the lifelong learning subjects that Texas Engineering Executive Education and Petex are working with subject matter experts in industry to develop new online content for. So today, I think we have a great topic to start the webinar series. We'll be talking with Dr. David Allen about Project ASTRA, which is a new, more robust sensor network for emissions monitoring, and really a great collaboration between industry and academia, as well as nonprofit sector. So UT Austin, the Cockrell School of Engineering, the Environmental Defense Fund, ExxonMobil, Gas Technology Institute, and Pioneer Natural Resources Company have all come together to get this project going. As I mentioned, I'm excited that David Allen is our first speaker because David is a fantastic educator, both at the university level and establishing those connections to the secondary system to make sure that we've got a pipeline of talent in addition to his research. So let me tell you a little bit about Dr. Allen, and I will hand off to him. So Dr. David Allen is the Gertz Regents Professor of Chemical Engineering here at UT Austin and Director of the Center for Energy and Environmental Resources. Dr. Allen's been the lead investigator for multiple air quality studies, which have had a substantial impact on the direction of air quality policies. He served on a variety of governmental advisory panels, and from 2012 to 2015, he chaired the U.S. Environmental Protection Agency Science Advisory Board. He was elected to the National Academy of Engineering in 2017. He has won teaching awards at UT Austin and UCLA. Dr. Allen received his BS in Chemical Engineering from Cornell University in 1979 and his MS and PhD degrees in Chemical Engineering from the California Institute of Technology in 1981 and 1983. He's held visiting faculty appointments at California Institute of Technology, University of California, Santa Barbara, and the Department of Energy. So with that, Dr. Allen, tell us about Project ASTRA.
Great, thank you, Eric. I'm going to begin sharing my PowerPoint. So I'm going to tell you about Project ASTRA, as Eric mentioned, but to make sure that we're all starting from the same page, I'm going to put Project ASTRA in context and talk a little bit about natural gas production, methane emissions, and climate, and how Project ASTRA fits into that. So for some of you, this beginning material will be a lot of review, but for others, perhaps it'll be new information. So natural gas production in the United States has been increasing rapidly. The U.S. has become the dominant producer of hydrocarbons in the world's largest producer of oil and natural gas. And that's largely due to the twin innovations of horizontal drilling and hydraulic fracturing that have enabled extraction of hydrocarbons from shale resources. Texas is leading the way in this with some of the largest production regions and also leading in the development of the technology. But that's another story for another day. Hydrocarbon and particularly natural gas production is increasing. Methane is the principal component of natural gas, and methane is a potent greenhouse gas. On a pound-for-pound basis, methane in the atmosphere produces 120 times as much warming as an equivalent mass of carbon dioxide. And if we look at the left-hand part of this slide, we can look at the warming effect of various atmospheric warming agents, both gases and particles, and how much they've changed with respect to the composition of the atmosphere prior to the Industrial Revolution. So if we take pre-industrial revolution levels in the atmosphere going back to roughly 1750, compared to the composition of the atmosphere today, and ask how much of that change, how much that change is warming the atmosphere, what we see is that methane contributes about a quarter of the total warming of the atmosphere today due to changes since the start of the Industrial Revolution. So there are lots of different ways thinking about why methane is important. This is one of them. And so where's all that methane coming from? This is an overview of what we know about methane emissions. The current best estimates are that the total amount of methane going into the atmosphere worldwide is about 558 teragrams, or 10 to the 12th grams, and about 60% of that is believed to come from human sources, the remaining 40% from natural sources like wetlands. Of the man-made sources, there are two primary contributors. One is agriculture and waste, particularly waste in landfills, and by far the largest part of that is agriculture, a combination of animals, their manure, and rice farming. Leads to on the order of 200 or so teragrams going into the atmosphere. Fossil fuel use collectively, both oil, natural gas, and coal, is believed to contribute about 100 teragrams per year. The numbers from each of these individual sources are not precisely known, but the total going into the atmosphere globally is known with a fair amount of precision. And if there are questions on that, I'll be happy to answer them at the end, but I wanted to put the contribution of fossil fuels to methane going into the atmosphere in context. It's about a third of the man-made contributions, and in turn, the man-made contributions are about 60% of the total methane going into the atmosphere. So fossil fuels are a significant component. How much do methane emissions influence the overall greenhouse gas impacts associated with natural gas use? Well, let's look at power generation, which has been one of the primary uses of natural gas in the United States. If we compare the emissions of carbon dioxide, greenhouse gas carbon dioxide, from an average power plant in the United States, we get about a ton of carbon dioxide for every megawatt hour of electricity that we generate from the fleet in the United States. In contrast, natural gas, when it's used for power generation in a modern natural gas plant, will release more than a 50% reduction, less than half as much carbon dioxide going into the atmosphere. However, as we've been noting, methane is important, and so carbon dioxide isn't the entire story. If we have methane emissions along the supply chain for natural gas, that can erode that carbon dioxide benefit that natural gas has relative to coal, and we can lose some of that climate advantage that we have of shifting from coal to natural gas. So how much methane would make a difference? Well, here I'm going to give you a slightly different number, and that is to tell you that over a 20-year period in the atmosphere, methane is 84 times as potent as carbon dioxide on a pound-for-pound basis. So why are there these different numbers? What's going on with this potency of methane relative to carbon dioxide? Well, carbon dioxide is quite stable in the atmosphere. It will persist and not react chemically for very long periods of time. In contrast, methane will slowly react. It reacts with primarily chemical species in the atmosphere called the hydroxyl radical, and slowly gets converted to carbon dioxide. The half-life of methane in the atmosphere being converted to a series of products that eventually lead to carbon dioxide is about 12 years. And so if we're interested in the warming effect over a long period of time, say 100 years, then a carbon atom initially emitted in a methane molecule for the first 10 years or so might be in that methane molecule, but going forward from there for the next 90 years, if we're interested in a 100-year time period, would largely be in the form of CO2. So if we're comparing methane to CO2, we need to specify what time period we're interested in. If we're interested in the immediate effect today in the atmosphere, how much is methane warming relative to carbon dioxide? It's 120 times as potent. If we're interested in a 20-year period, it's 84 times as potent. If we're interested in a 100-year period, it's on the order of 28 times as potent. So methane is a potent greenhouse gas, but exactly how potent depends on what time period we're interested in. But let's get back to that question, how much methane emissions will make a difference? So this is an analysis that was published now 8 years ago by some of my colleagues at Environmental Defense Fund together with researchers at Princeton. And what this does is compare various technology shifting scenarios. So let me refer you to that top graph on the diagram, the top line on the diagram. And so let's look at the origin with 0 on the horizontal axis. And what this plot tells us, this upper line on this plot tells us, is that if we have methane emissions that amount to 2.7% of the methane leaving a wellhead, and 2.7% of it escapes before it gets to a power plant where it's going to replace coal as the fuel for the power plant. If those emissions are 2.7% or more, we lose all of that CO2 benefit that we had from the more efficient power plant and less CO2 emissions from the power plant. On the other hand, if we're willing to look over roughly a 100-year time period and only consider that methane is perhaps 28 times as potent rather than 120 times as potent as carbon dioxide, then the threshold of leak that we can accommodate and still get a net climate benefit is on the order of 6% or more. So how much methane emissions will make a difference? What I'll refer to here is if we want an unambiguous climate benefit, if we want to say there's a climate benefit no matter what period of time we're interested in, we'd better get below about 3% from wellhead to burner tip. So what are the emissions? Well, prior to 2012, we really didn't have a good idea, but the best estimate that we have right now is about 2% in the US. This is a national average. It's based on data that my group, among others, have collected over the last 8 years or so, and it is the estimated percentage of the methane that leaks from wellhead to burner tip. We haven't sampled all 500,000 wells in the United States that are actively producing natural gas. And so there are different ways of extrapolating the data. And so you see this range of something like 1.7 to 2.3%. But best estimate is on the order of 2% of the methane leaving the wellhead gets into the atmosphere before it gets to the burner tip. So for coal, we still have a climate benefit, but we lose much of that advantage that we had from lower CO2 emissions. For switching from gasoline or heavy-duty diesel to natural gas fuels and transportation uses, we need to get to a much lower leak threshold to have an unambiguous net climate benefit. And so that 2% leak rate may use up all of the CO2 advantage that we have for technology shifting like gasoline or heavy-duty diesel to natural gas. So 2% is a number that we'd like to get lower. So how have we arrived at this? Well, since 2013, there have been a series of extensive measurements reported by my group, by others. They've been based on the types of measurements that you see depicted in the pictures here, ranging from going directly on a site and making measurements of the methane, to putting fixed sensors out there, to driving vehicles downwind of sites, to flying aircraft over various regions that might have emissions, to using satellites. And so a combination of all these data has led to that current understanding of what the average emission rate is. But an important thing to note is that averages don't tell the whole story. So all these measurements over the last 8 years or so have led to the conclusion that in the United States, where almost all of this data has been taken, we estimate that about 2% of the methane produced escapes to the atmosphere before the burner tip. The International Energy Agency has done international projections and estimates also a number of about 2.7 or 2%, more precisely 1.7% on a global basis is being emitted before the methane reaches the burner tip. But an important part of this finding is that not all sites, not all equipment emits equally. For example, 2% of the sites in the Barnett Shale in Texas lead to 50% or more of the emissions. And that's true in virtually every production region that's been measured in the United States. If we look at specific pieces of equipment like pneumatic controllers, 19% of the pneumatic controllers lead to 95% of the emissions, and so on. We could talk about compressors and all sorts of other sources. In all these cases, a small subpopulation of sites or pieces of equipment lead to the majority of the emissions. And often these are malfunctioning devices. And so if we really want to make progress on reducing methane emissions, what we really need is a strategic approach to targeting high emitting sources. We need to find these high emitting sources, for example, in the Barnett Shale, the 2% or so of sites that have the most emissions, and then really fix them quickly and drive emissions lower in that way. For the last 8 years or so, what we've been doing is very labor-intensive processes, going out and making these measurements at a variety of different types of field operations. And operators of facilities in natural gas supply chains typically go out and once a year or once every 6 months or once a quarter will send operators out doing what you see in the photo on the left here, using an optical gas imaging camera or another technology to go out and look for emissions. Those are some of the technologies we used in our field studies to make measurements. And so that's a very labor intensive and very expensive process. So the techniques that we have right now for finding these high emitters very quickly tend to be very expensive. The EPA has estimated that going to a site for these inspections costs about $1,000 per site per year. And if you then say, well, in the Permian Basin, we might have 200,000 sites, that's $200 million a year that we're spending looking for these high emitters. And most of the time when an operator goes to a site, they're not finding anything. So can we spend those resources more effectively? And that takes us to Project ASTRA. So once we find these emissions and fix them, there are regulations that are potentially driving these measurements that might begin to occur more frequently. There are large customers, and here I've just given one example, that are interested in the greenhouse gas footprints of the natural gas that they purchase. So a number of drivers trying to take us to more efficient ways of identifying emissions. So let's look then at Project ASTRA. The team that's working on this believes that we're at an inflection point with the technologies, that between sensor technologies and data analytics, that we're at a point where we can invent new ways of going out and finding these high emitting sources and drive natural gas emissions lower. So what we want to do with Project ASTRA is transform methane emission detection from very labor-intensive surveys that are inefficient and relatively slow to repair emissions to a sensor-intensive, near-continuous monitoring system that will efficiently deploy operators to sites that have unintended emissions. So instead of visiting every site on a fixed schedule, looking for these high emitters, we go only when the sensor network tells us there's evidence of unintended emissions at these sites. And we believe that at the same cost as current surveys, that we can quickly find and repair emissions. That's the essence of Project ASTRA. So how do we get there? Well, before I talk about the steps getting to the launch of Project ASTRA, let me talk about the transformations it involves. Instead of individual monitoring by individual companies, what it means is a shared network in production regions. Instead of infrequent monitoring, going once a year or once every 6 months to sites, it means near continuous monitoring. Instead of going site by site, we have continuously a distributed network of sensors that are simultaneously making measurements everywhere. Instead of each company paying for operators to go to their individual sites, we can share the costs among multiple operators in the production region and share innovations. So how do we get there? We have a website for Project ASTRA, and so if you'd like more details, you can go to that website that has the public information that I'm describing in this talk today. And the partners for Project ASTRA, as Eric mentioned in the introduction, are Environmental Defense Fund, ExxonMobil, Gas Technology Institute, Pioneer Natural Resources, and the University of Texas. So our goal is to get to step 3 in this slide. By the second half of next year, we want to deploy in the Permian Basin in a region that encompasses approximately 1,000 wells and all of the midstream facilities that go with 1,000 wells. We want to deploy a sensor network and test it. Begin deploying it in the second half of 2021 and continue operating it throughout 2022. That's the point we're aiming for by this time next year, is to begin that deployment. How do we get there? Well, there are 2 critical steps that we're working on right now to get there. The first is to test the sensors. I can go to Home Depot today and spend about $50 or so and buy a methane sensor that I can put in my home and detect a natural gas leak. Equally, I can go out and buy the best available sensor on the market and spend about $200,000 doing that. And we've done that for this methane sensor intercomparison that we're about to run. And we have everything in between. We have all sorts of different sensors at all sorts of different technology readiness levels with different sensing mechanisms and capabilities. And what we need to understand is how many of those are ready for prime time in a sensor network like ASTRA. So we're going to be conducting, beginning in August, the West Texas Methane Showdown, where we will be testing between 6 and 8 different sensors that have gone through an application and review process that we've been conducting. We will test over a 6-month period the ability of these sensors to operate unattended in field operations, and their ability to deliver accurate data and precise data. And so we're going to be testing the sensors over a 6-month period from the heat of August and September to the snows of February out in the Permian Basin. The next thing we need to do is to design the network, and this is a particularly difficult challenge. And so what we're going to be doing is creating for this pilot region that encompasses on the order of 1,000 wells, we're going to be building a digital twin. The digital twin will consist of a couple of different parts and be used for a couple of different purposes. The couple of parts that the digital twin consists of is first an emission model. If we're going to be sensing minute by minute out in the Permian Basin, we need to know what normal emissions are, and they're quite complex. We need to know what normal emissions are for all these sites in our test region. So over the last 4 years or so, with support initially from ExxonMobil and then from the Gas Technology Institute's Collaboratory to Advance Methane Science, or CAMS, which has 7 industrial sponsors, we've been developing an emission model that's about to go into public release that allows us to predict minute by minute what emissions are under normal operations. We're then going to take those emissions, take that model, predict the emissions for our 1,000 test well region and all the midstream facilities, and predict what the emissions are minute by minute in our test region. We'll then couple it with atmospheric models that will tell us in 4 dimensions, 3 spatial dimensions plus time, what concentrations of methane and ethane and propane and butane and other compounds will be in the atmosphere. So we will create a synthetic atmosphere, and we'll put normal emissions into that atmosphere, and then we'll put the emissions that we'd like to be able to detect into that synthetic atmosphere, into that digital twin. We'll put in unlit flares and their emissions. We'll put in malfunctioning pneumatic controllers. We'll put in open thief hatches. Take your pick on what type of unintended emission you're interested in. We will put those into the model and see what that does to atmospheric concentrations and understand where we need to put the sensors and how precise the sensors need to be in order to detect these unintended emissions. What we'll also do with the model, in addition to designing the network, is try to understand what the data analytics will be. And so how do we take streaming data from 500 or so sensors deployed in this region and understand what emissions are minute by minute at all of the points that we're interested in the region, and compare that against normal emissions and decide at the moment, where should we send an operator to look for unintended emissions? So that's an overview of Project ASTRA. Let me dive a little bit deeper into each of those elements. So first is the West Texas Methane Showdown. We're doing that right now. So we're testing sensors. I think this is pretty straightforward. So I'm just going to describe that we're doing it in the Midland Basin near Midland, Texas. We have all the applications that have just come in. We're anticipating the sampling will begin in approximately August, depending on the COVID situation. It'll last for 6 months. We'll be downloading all of that data and comparing all the sensors. We'll be providing calibrated challenges to the sensors and doing continuous intercomparisons with what we think is the best methane sensor on the market. And we will be doing that on a production site, a single production site out in the Midland Basin. The sponsors for this intercomparison you see listed here. So they're AT&T, who's interested in the communications bit of this, as well as the Collaboratory to Advance Methane Science. And you see listed the 7 companies that support CAMS, the Collaboratory to Advance Methane Science. And then our core sponsors are also supporting this West Texas Methane Showdown. Then we have the Digital Methane Challenge. So this has those 2 parts. First is the emissions, then the atmospheric modeling, and 2 purposes: design the network and the data analytics. We're releasing the emission model right now, and over the latter half of this year, we'll be creating this digital twin. Let me try and begin to describe to you why this is such a hard problem, though. So imagine that you deploy a sensor network, and here I'm actually showing a graphic from the Barnett Shale. So imagine that in the Barnett Shale, you deployed a sensor network and you could anticipate that you could get a profile, a mapping of methane concentrations from the sensors that looked something like what you see on the right. You now need to invert that and convert that to emissions at each individual site. And then you need to compare that to normal. So what does normal look like? And so I'm going to show you an animation showing normal for the Barnett Shale. So this shows hourly instances of emissions. And so you're looking down at the counties in the Barnett Shale. And what you're seeing here then is the fluctuation hour to hour. Now we have the ability to do this minute by minute or even finer time resolution, but this is what normal looks like. And so if we're looking for unintended emissions, we need to separate that from what normal looks like. And you can begin to get a sense of how challenging this problem is. And this is just the first part of the problem, predicting what the emissions are. What if we superimpose on this an atmospheric model? So now I'm showing you some modeling that we've done of the Eagle Ford. So now we're looking, again, the dark lines that you see here are county boundaries. You're looking at the Eagle Ford. What you're seeing in the image in the grayscale is what intended emissions might, or intended concentrations from intended emissions might look like in the Eagle Ford. Here, the wind is blowing from the southeast to the northwest, so you can see the plumes in the grayscale. But what if we put a couple of different types of emissions on top of this? What if we put a liquid unloading into this? What if we put a stuck separator dump valve into this? What would that look like? And this animation will show you color scales that are on a slightly different scale than the grayscale, but will show you these emissions appearing. And so what we want to be doing is looking for things like you'll see popping up here associated with a stuck separator dump valve or a liquid unloading. Hopefully from this animation you get a sense that, well, there are characteristics to these, including how long they last and what their variability might be, but separating these unintended emissions in the atmospheric concentrations from the intended emissions are things that we want to be able to do with this synthetic data set. And we think that this is going to be critical both to the design of the network as well as to the data analytics. And then once we have the design, Once we have the synthetic atmosphere and come up with a design, then in late 2021 to full deployment in 2022, we'll be building out that network in the Permian Basin over a test region in the Midland Basin, encompassing roughly 1,000 wells. So here's a timeline of where we are and where we want to be. So we're beginning the West Texas Methane Showdown right now, and that'll be going on for the next bit. We're also beginning to conduct the Digital Methane Challenge, and then Project ASTRA deploying in the second half of 2021 and into 2022. And with that, I'm going to conclude. In a moment, I'll turn it over to Javier to the questions and trying to answer your questions. But the primary goal here is to see how much we can drive methane emissions lower, going from that 2% level that is the current state of affairs in the United States to perhaps half of that, even lower, and improve the climate benefit of natural gas as a transition fuel to a lower greenhouse gas emission energy system. So with that, I'll open it up to questions and look forward to answering your questions about Project ASTRA.
Thank you, David. So let me start with a question I have. And I'm getting a little like myself, but I'm going to go ahead and just ask the question. Can you share any details on the digital twin models regarding the algorithm selection? Are you looking for more AI type based algorithms like neural networks, or a more physics based deterministic algorithm?
All right, so the algorithms and the data analytics are going to be a core part of this challenge, and we're going to be addressing this. Current plan is to proceed along two paths. What we want to do with Project ASTRA is to demonstrate that a widely deployed, spatially dense sensor network can lead to identifying unintended emissions much more rapidly and at the same cost or lower as the existing approach of sending operators out for leak detection and repair. And so our goal as a Project ASTRA team is to identify a solution that will drive us to meeting that benchmark. We believe that there are going to be many, many different approaches. And so we are going to be employing a particular approach. And we're going to experiment over the next 6 months with multiple approaches with the synthetic atmosphere. And we will select a design of the network that goes along with the data analytics and have a inversion algorithm that we think will be efficient enough to demonstrate what we want in parallel with that. So we want to come up with a practical solution that hasn't been committed to yet. We're going to explore a number of options, hasn't been committed to yet, but in parallel with that, what we're going to be doing is releasing our synthetic data set together with scenarios of unintended emissions as training and learning data sets to allow people who have great ideas on the analytics to use those ideas and hopefully come up with better solutions than our project team is able to come up with. If better solutions can be found, great. and that'll advance the science of this even further. But what we're concerned about, what we don't want to do is have that competition and have that competition be on the critical path to deploying the network and demonstrating proof of concept for the network. So we'll come up with a solution. It may not be the best, but we'll also release our synthetic data sets to the broader community to hopefully identify even better solutions. So 2 paths.
Well, thank you so much, Dr. Allen. We have another question. How are you measuring the escaped gas from ESD, emergency shutdown events, at large compression stations, as well as transmission line blowdowns for inspections?
So I'll interpret that question in a couple of different ways. So one way to interpret that question is, well, how were these measured in the field studies that went out and tried to quantify the result and give us the results that I described in the first half of this talk that got us to the point where we think we have sort of an average understanding of where emissions are coming from in the United States. And often for those particularly large events where you can't go right at the emission source and make a measurement, what was done typically was to use what's referred to as a tracer technique. So what you do is you set up a couple of sensors, very sensitive sensors, downwind of the facility. You release a known flow rate of a gas that you can detect very precisely, often nitrous oxide, N2O. You're releasing that at a known rate. You go downwind and you measure the ratio of methane to your tracer gas. And because now you know the release rate of the tracer gas, you're able to get at the emissions of the methane. And that's the approach that's generally been taken in doing these quantifications for very large emission rates, simply because of safety issues with getting right up to the source and doing source sampling. For going forward with Project ASTRA, the things that we're going to be looking for are both intended and unintended emissions and separating those two. And the really big sources, our goal with Project ASTRA is to identify those facilities where we think that there is, at the moment, a high probability of unintended emissions, and to deploy operators to those facilities. And so what we're going to be looking for, and one of the reasons we're choosing the region we are choosing, is because we'll have good operator cooperation to provide us with activity data. So if they're going to do a liquid unloading or a blowdown of various types, we'll have that information and be able to incorporate that into our predictions of what normal emissions would be. And our goal then would be to identify, perhaps not exactly quantify, but identify what the locations that have a high probability of these unintended emissions.
So, David, I'm gonna combine a couple questions here around scope and scale. Bob Harkey points out that much of the on-stream operations starting in the 70s, right? The assets have changed ownership many times. There's been a lot of fragmentation of the operating assets, and the culture driving operating costs to a bare minimum has created multiple sources of methane emissions. That combined with kind of the partners you have at the table already, how's this fragmentation going to affect Project ASTRA, and and how much of the basin ultimately you're going to be able to cover?
Well, the goal of Project ASTRA, as I showed on one of the earlier slides, step number 3 was to do a demonstration, right? And we picked our demonstration region because we want to demonstrate proof of concept. You demonstrate proof of concept, in our case, by picking a region where 90% of the wells are operated by our partner companies. And so we're going to have, in that test region, we're going to have good activity information on the vast majority of the facilities in that test region. Further, we're picking the Permian Basin for a couple of reasons. One, it's really important, but second, you know, from an atmospheric modeling point of view, if you can't model things in the Permian Basin, you can't do it anywhere. Topography is flat, the sites are dense, the wind blows really well, giving you nice plume setup. It's not the Marcellus in West Virginia, right? And so we picked the Permian Basin in part for that reason as well. So if we can, our initial goal is to demonstrate that we can do this at our cost target. And so we picked our demonstration at the moment being an easier part of the problem. However, the question points out a really important thing. If you want to take the next step then and go from proof of concept to deploying this in 20% of the Permian Basin or 50% of the Permian Basin or all of the Permian Basin, then you're going to need to recognize that you're going to have a huge diversity of different operators. And the amount of information you're going to have about the activities that are going on at those operator sites is going to be quite different in these different regions, depending on what the spectrum of field sites are. And that might allow you, or it might require that you use different data analytics than you would use for an area where you have really precise knowledge about the individual operators. Our current thinking is in thinking about how do you do the data analytics. It's informed by lots of really good operations data. But let me draw an analogy for you that came up in a previous briefing about Project ASTRA. I can build into my home today a system that senses my water usage, that will sense my water usage and over time develop enough of a knowledge base about my water usage in my home such that after a learning period, it would be able to identify, oh, I have a water leak. The water usage pattern that I'm getting right now is completely different than what I've had before, without getting any direct information from my dishwasher or washing machine or anything else in my house, and shut down the water to my house based on that. So in the absence of really good operator data, we still think there are pathways in the data analytics to getting to prediction of where you might have high unintended emissions. But that's not the easiest problem to solve. And we're going to start with proof of concept with what we regard as the easiest problem to solve.
Great, thank you for that. And we have one last question. It's regarding sensors. So you mentioned some sensors that you were discussing, but Mike has a question about how do you register those sensors? Does a well have to actually producing to register as an emitter?
So let me first say that we're not necessarily thinking about putting sensors at every site. Right? So one of the advantages of this network is that instead, because it is a shared network in a region, we don't necessarily need to have a sensor at every site. Now, in the emissions model, what we've been doing is taking data from places like the Railroad Commission and making sure that we are identifying all sites that, for example, in our test region have had production over the past 5 years. And so we're identifying all those locations and getting the most current activity data from all of those sites and putting all of that into our emissions model. But we don't need to put a sensor at every site, and that's part of the efficiency of the network. So we're not going to say, well, you know, we're putting a sensor on every pad, and therefore we need to determine what's an active pad and what's not an active pad. We need to distribute them so that based on what we understand to be the emissions over the period of time that we're going to be doing the sensing, as well as recent history, that we'll be able to sense all of the emissions from all of those facilities.
All right. Well, David, I know you have a hard stop. So I just wanted to thank you very much for this fantastic presentation. In the space I live in, the continuing and professional education world, and being a chemical engineer, the work we do with the petroleum extension with Petex, making sure that people have the right skills and knowledge about petroleum measurement and natural gas measurement, and the work we were doing out in the Permian, as well as all of the engineering education and executive programs we have. This is a perfect fit. I could see us right in the middle of that Venn diagram with Project ASTRA. So for those of you that have asked along the way, we will be publishing this webinar, the recording, and we'll send you a follow-up link so you can find it. And with that, let me hand off to Canavis for wrap-up. So thank you again, Dr. Allen.
Thank you.
Yes, thank you, Dr. Allen, and thank you for everyone that participated in providing questions and Q&A. Sorry we couldn't get to all of them, but we are conscious of your time, and we wanted to first acknowledge and recognize all the units of the Cockrell School of Engineering that had a part in putting this wonderful program together. First is the Texas Engineering Executive Education Program, and they specialize in reskilling and upskilling companies' current workforce through our master's degree programs, graduate certificates, short courses, or custom courses on company sites. So if you have a need under the STEM umbrella where you would like education or training, this will be the perfect opportunity for you to contact our department. And next is the Petroleum Extension, which is Petex. Petex has been around for over 75 years, serving the oil and gas industry through e-modules, publications, online, and in-person training. So if you have a need anywhere in the world for the oil and gas training, this is the department for you. And last but not least is our Research Relations Department. Our Research Relations works to solve some of the world's biggest problems around water, technology, emissions, all of that under the umbrella, and many more. So if you have a need or would like to support research from faculty and staff, Research Relations Department will help you do that. All of us as a unit, we're here to serve you as a community. We love to be a part of the projects you have and help you reach your full potential in education, training, and research. So if you have an idea or a topic that you would like us to discuss in the next TexTalks, we would love to be a part of that. So feel free to complete the survey that will shortly follow this presentation. Next, we want to make sure you're aware. Our next Tech Talks will be July 10th with Kerry Malone. Kerry Malone has over 40 years of pipeline industry experience, where he will talk to us more about the pipeline right-of-way, how it affects you, how it affects your business, and how it will affect the future. So if you have the opportunity, join us on July 10th at 10 a.m. to talk about pipeline right-of-way. With that, we're happy to have you join us today. We love to be a part of helping you reach your full potential. And if you have anything else, feel free to contact us. Have a great weekend and hook 'em horns.